Hi, this is Pikachu here, and today I'm gonna show you my workout routine, which is doing integrals. And you may say that math doesn't give you muscles, but clearly you just haven't done enough math, and today I'm gonna show you. Let's start. Let's start with a little graph. Let's have y is a function of x, and let's try and calculate the area under this curve. How do we do that? Well, we don't know. And when we don't know, what we can do is approach it with things that we already know. So we know how to take the area of a circle, a triangle, and a rectangle. And the way this can help us is that we can draw rectangles inside this graph. And as you can see, we can approach the shape of the curve pretty close. The only problem is these empty spaces over here. This is our margin of error. Well, how do we get rid of it? Well, one way that we can reduce it is to draw thinner rectangles and more rectangles. As you can see, we are getting a lot closer to the shape of the curve. The problem is we still have these empty spaces. Even if they're really small, we're still not getting the exact area. Well, let's go back to when we had just a couple squares, just a couple rectangles, just to make it easier on us, and try to get a formula out of that. So we know that the area of a rectangle is the width times the height, and the width here is gonna be x1 minus x0, or in other words, delta x. And the height, well, that's gonna be just f of x. And that's the area of one of our rectangles. So let's write it in a formula. And that's going to be the area is equal to fx times delta x. However, that's only for one rectangle. So let's make it the sum. And here we have the sum of, let's set j equal to 1 and make f of x j times delta x of j. And now, to what do we make the sum? Well, right here we only have 3 rectangles, so we should write 3. But what we're trying to do is come up with a general formula to get the area. So let's just make it n for now. And what number do we use for n? Well, we know that with more rectangles, we get a closer approximation to the curve. So what number do you use? 100? 1 million? Well, what we need to do is use infinity. The only problem is, if we use infinity, an infinite number of rectangles is going to result in the rectangles being so small that they basically become 0. And if they become 0, well, we don't have an area. Thankfully, we already have a tool for that. That's called the limit. What we need to do is take the limit as n approaches infinity. This way, we're getting the value of infinite number of rectangles without it actually becoming 0. And that way we can get technically the exact area below the curve. However, we have a tool for this when we take the limit of a sum, and that is called an integral. So let's rewrite it as the integral of f of x. And instead of delta x, since it's a change in the x, let's write it as dx. And how do we define the integral? Well, since it's in terms of x, we can just use x0 and x1. And that's pretty much it for this formula. The reason this is probably my favorite one is because this problem is the one that led to the development of integration. Okay, so for our second problem, we are gonna use the same curve, but instead of trying to calculate the area below the curve, we're gonna try to calculate the length of the curve itself. Now, how do we do it? Well, we don't know, but we can approach it just like we did last time. Instead of rectangles, however, let's try to use tangent lines. Let's try to draw tangent lines that follow the curve like this. And as you can see, they follow the shape pretty close, but they're still not it. Well, you may say, can we just multiply to infinity and make the tangent lines infinitely small but not zero, just like we did last time? Yeah, we can do that, but the problem right now is we don't know how to get the length, or in this case, let's call it delta L since it's a change in the length, or we can do it as the L. Well, let's go back to a simpler example that we did last time. Instead of many tangent lines, let's use just one big one. And if you think about it, each line has an x and y component, which means that we can just use Pythagorean theorem to get the value of the L. So let's do that and put it in a formula. dl is equal to the square root of dx squared plus dy squared. And that's the L. And all we need to do is, just like we did last time, we can just use an integral and integrate the L for the value of the entire curve. However, we can't use the x values as we did last time because this is in terms of L, and we don't know the values in terms of L. You might want to just calculate the values in L, but an easier way is to convert the L and see the equivalent when you have it in the x. And all we have to do is solve for the x. Now, we're only solving for the x because y is a function of x. If you had x as a function of y, you want to solve for the y. But for this time, we're solving for the x. And if you get the opposite occasion, all you have to do is switch the places of the x and the y. So let's do that. And just rewrite the dl as square root of the x squared plus dy squared. Now, how do we take dx out of here? Well, let's try to factor it out first. dl is equal to the square root, factoring dx squared as a whole, and dx squared over dx squared, that's just gonna give you 1. So that's gonna be dx squared times 1. Then plus dy squared. dy squared over dx squared. Well, we don't know what that is yet, but we can just write it as it is. dy squared over dx squared. But remember, in a fraction, if you square the top and the bottom, it's the same as if you square the whole thing. So that's what we get. Now that we have dx squared multiplying that other factor, we can just square dx squared and take it out of there. So dl is equal to the square root of 1 plus dy over dx squared times dx. And there we go. There's the dx. And we know that dl is equivalent to all of this. So all we need to do is now substitute it in our previous integral, which would be instead of dl, we would have all of this square root of 1 plus dy over dx squared dx. And now we can use x values here in the definition. We can use x0 and x1. There you go. Okay, this is our third problem. and we're gonna use the same graph, y being a function of x, but this time we're gonna try and do something more interesting. We're gonna rotate the curve, the arc around the x-axis. Now if you use your imagination, it's gonna become a mirror image on the bottom, and overall it's gonna be a 3D body. However, you don't have imagination. Let's try to draw it in 3D like this. And there's our 3D body. Now let's take a closer look. You can see it has the same shape from this perspective in this axis. However, if you look at it from this side, it is basically a circle, and we have to keep that in mind for what we're going to do later. So what do we want to do with this body? Well, what we want to try and do is calculate the surface area, which is basically the blue part. And it may look pretty intimidating right now. So let's try and come back to the 2D world and see how we can approach it. Well, let's approach it how we always approach the problems. For example, the last two times, what we did was segment. We ended up segmenting the entire thing into many small sections. However, let's begin with a big section because it is always easier to work like that. Let's do it like this segment over here, and remember that this is a 3D body. What we want to calculate is this part over here. Rotate it, nothing in the middle, just this part, this piece of the arc, which would end up being this piece too. How do you get that? Well, remember that this part is basically just a little piece of the arc, a tangent line, as you can imagine. And we already did that in the last example, so let's write it as DL. Let's write it as DL. How does that help us? Well, when we rotate it, and let's go back to 3D. Okay, we are back in the back to the 3D world, and remember, as you can see, it's a circle if you view it from this side, and this circle is the DL rotated, and we know how to calculate the perimeter of a circle. It's basically multiplying the radius, which is this, times 2 pi, since this distance is pi and this distance is pi, so it's 2 pi. Now, what do we do? Well, r is equal to f of x, or y. R is equal to f of x or y. And then we have this is gonna be dl and 2 pi, and the perimeter of a circle is 2 pi times the radius. But since we're in 3D now, we understood that what we need to calculate the area of one of those truncated cones is 2 pi times the radius. Radius is equal to y, or fx, and we are going to stick with y, and we'll see why later. No pun intended. And that's times the L. And that's for one of them, so we are going to integrate it, and that is going to be equal to the total surface area. What else can we do? Well, we know dl, so let's just write it as a substitution. So 2 pi times y times the square root of 1 plus dy over dx. And remember, we're using the dx form of the dl because the function is a y as a function of x. If it were x as a function of y, we would use a dl in terms of dy. I'm sorry. Okay, so this is basically it. However, there's one problem. Y doesn't work with dx, but we do know that y is equal to f of x. So in this case, we're gonna cancel it and put it as f of x. But why did we insist to use y before? Well, that's because in this rare scenario that the function was giving x as a function of y instead of y as a function of x, well, this right here, this wouldn't be dx, this would be di, and this would be dx over dy. In that case, we couldn't just use y instead of fx. We can directly use y, and we would just save so much trouble instead of just inputting fx and going through more calculations. So that's the reason why we use y, and then we substitute it. But anyway, let's get rid of all of this smudginess and write the final equation. The sum of all of these cones, which is equal to the surface area of the curve rotated, is equal to the integral, since we're adding them up infinitely times, of 2 pi radius is equal to y and dl. And we can just write it as this. This is the formula for our curve rotated. However, this is a very specific case. We are only using y because y turns out to be the radius. If we were rotating around the y-axis, in that case, our radius would be x. And if it was x as a function of y, in that case, this wouldn't be dx and this would be dy. Well, let's even write a simpler formula. Let's write the surface is equal to the integral of 2 pi times the radius of dl. And that way we can use this formula for any of those cases. And that's it. Hopefully by now you're as muscular as I am. If not, just keep doing more integrals.